Okay, here we are back again, Physics 125, Lewis and Clark. This is Chapter 8, the first lecture. We're going to cover this chapter in 2 lectures as we normally do. This chapter is called Work and Energy. And just a brief review, again in Chapter 4, we learned about motion, descriptions of motion. Chapter 5, we talked about forces, Newton's 3 laws, the things that cause motion. And then we discussed the fact that acceleration is complicated in many real-life circumstances. It's not always constant. And so we kind of went into a series of different chapters where we were trying to get around the fact that acceleration is complicated. And this is kind of the pinnacle of that. We did momentum, we did statics, and now we're going to do work and energy, which is a great way to get around the fact that our accelerations are often not constant, and that's challenging for us mathematically. So work and power and energy, they're all related here. So we're going to start off with a discussion of work. Again, it's one of these terms that's handy and not handy when it comes to discussing physics. It's a word that's very prevalent in our everyday society, but our everyday society has changed the meaning a little bit from what work means in physics. So you got 2 pictures here on the screen. We got a guy who's working on papers with a calculator and another guy who's swinging his axe at a tree. And we would say both of them go to work, but physics would say one of them is doing significant work and the other one is not. So you see there on the screen, there's a link to a video. We've watched a couple of Eureka videos before in this class. There's actually 3 Eureka videos that correspond to this concept, this content in this slideshow. So I'd like you to click on that link and watch just the first 5 minutes, just the first 5 minutes of that video, and then we will move on to my explanation. But keep that video open in your browser because we're going to come back to it and watch some more of it a little bit later, because it's got a section on work, section on kinetic energy, section on potential energy. So now that you watched that video, they taught you, of course, that work is equal to force times distance, and that force and the distance has to be going in the same direction. And a really big idea is that if you have no distance, you have no work. No matter how hard you push, no matter how much effort you feel like you're putting in, if the object does not move, just like the strong man trying to push his car out of the mud, you have no work being done. So here the force and the distance have to be in the same direction. This is actually exactly the opposite of what we just learned in the last chapter with torque, where the force and the distance had to be perpendicular. So we have Newton meters again, but we're not going to leave it as Newton meters. We're going to put the newtons and the meters together, and we're going to call it a joule. So when we have a Newton times a meter, when they're in the same direction, and by same I mean parallel as opposed to perpendicular. So here we have force, distance, same direction. That is going to be work. Force and distance in different directions, that's not going to be work. So, and this is just, you know, it's talking about us applying a force, causing a change in an object's motion, and a way for us to measure that, right? Again, we talked about this a little bit in chapter 6 with the idea of impulse. How long do you apply your force for? Here the discussion is how far do you apply your force for? And it's a similar effect, but it's subtly different. So how much work is done on a 100 Newton boulder that you carry horizontally across a 10-meter room? So can you do this problem using the equation we just learned on the previous slide with force and distance? So most people take 100, they multiply by 10, they get 1,000, and that is the incorrect answer, because the weight of the boulder is pushing down and we are carrying this horizontally. So those two are not in the same direction, therefore work is not done when you carry an object horizontally. I point this out to my high school students. My classroom is on the 3rd floor. I point out to them that as they climb the stairs to my classroom, they are doing work on the books in their backpack, but as they walk down the horizontal hallway to my door, they are not doing work. And if you think about that physically in your life, you can relate to that. Now, you might be doing some work against friction, air resistance type friction, and there might be some fatigue in your muscles because you have to continually apply an upward force of 100 newtons to keep the boulder from falling on your foot, but you are not actively lifting the boulder, therefore you are not doing work on it. So how much work is done when you lift a 100 Newton boulder 2 meters? Well, now we have the force and the distance in the same direction, and so it's simply force times distance, and that is 200 joules of work. 100 times 2 is 200 joules of work. So we talk about work, and work is about lifting things, moving things, but if you look carefully at the work equation, it's force times distance. There's no component of time in that equation, and we care very much about time in our society. That's why we all have microwaves, because we care about how quickly things get done. And so we have a different unit for the rate at which work gets done, right? A rate is anything where you take the amount and you divide it by how much time it takes, and that's considered the rate. So power is the rate at which work is done, or the rate at which energy is consumed or generated. So it's simply you take your work value, you divide it by the time, and it's that simple. The units of power are watts. That's what we primarily use, the SI system. In the English system, we have foot-pounds per second, and in the English system, we also have horsepower, which is 550 foot-pounds per second, or 746 watts. This introduces a bit of a challenge. The math of power is not difficult at all. It's simply the work divided by the time, and we're going to do a couple practice problems there in a moment. But the difficulty that we get in this chapter with our discussion of power is what does W stand for, right? Up here in this yellow equation, the W is standing for work. But down here, the W is standing for watts. So W can stand for work or it can stand for watts, and it kind of depends on the context. The problem is these two things are very closely related in context, and it gets even more complicated, right? A work is a force times a distance, and as we already made reference to lifting the boulder, often the work we do is because we are lifting something, and when we lift something, we have to apply a force equal to that object's weight, and so sometimes we have weight that is another W. And so we end up with 3 different W's in this chapter: weight, work, and watts. They're all represented by a capital W, and that's very confusing. It's just the way physics is. I'm not allowed to change the symbol for watts. They don't let me do that. So I'm just making you aware of it so that you can be careful when you see a W to make sure you know which W that is and what it's supposed to stand for. So we have the electrical company, right? Some people call it the power company. Some people call it the electrical company. Not very many people call it the energy company, but really it's more about the energy they produce than it is about the power that they produce. It's a bit of a catch-22. They got to deliver that energy in good time at an appropriate rate for us to be able to use it. But really, most of us buy our energy in terms of, or buy our electricity in terms of the energy we use, not the power. There are some very large customers that get charged based on what their maximum usage in a period of time is, but most of us based on our total usage in, say, a month. So one of the reasons I think we have this phenomenon where we call it the power company instead of the energy company is because of the unit that they use, right? A kilowatt is a unit of power, right? It's got the watt right in there. Watt is a joule per second. It's a unit of power. A kilowatt simply means 1,000 watts. So a kilowatt is 1,000 watts. But if we have a kilowatt hour, which is what we actually are charged for on our electrical bill, some number of cents per kilowatt hour. Power is energy divided by time. It's in watts. If we bring a time unit back over and put it with the power, right, multiply it by the power, kilowatts times hours, we've now moved the time unit over here. We're no longer an expression of power. Remember, power is energy divided by time. Energy divided by time times time, the time cancels out. And what we are actually buying when we pay for kilowatt hours is energy, not power. Why don't they just do joules or megajoules? Well, they don't. They use kilowatt hours because they think that's clear to their customers. Their customers' light bulbs are rated in watts. Their their air conditioner, their refrigerator are rated in kilowatts. And so there's some concept then of if my refrigerator runs for 6 hours a day, it's going to use this amount of kilowatt hours. If you had a parent like I did who was always after you to turn off the lights because you were costing them money, nowadays the kids tell us to turn off the lights because we're ruining the environment. Back then our parents told us to turn off the lights because we were costing them money. If you had a standard bedroom light that was, say, had 3 60-watt bulbs, that would be 180 watts. So if you left your bedroom light on during the dinner hour for a whole hour, that would be 180 watt hours, which would come out to be 0.18 kilowatt hours. And here in Illinois, we pay a relatively low price of 5 to 7 cents per kilowatt hour for our electricity. So at 5 cents per kilowatt hour, leaving your bedroom light on for an hour would have cost a penny. And now that we have compact fluorescents and LEDs that are even lower wattages, we're using even less electricity. I'm not promoting leaving your lights on. I'm just saying it didn't cost my parents as much as they made it sound like I was costing them when I left the lights on. So here's a practice problem for power. A box that weighs 575 newtons is lifted at a distance of 20 meters. So we're lifting a box, therefore we're doing work on it. It's being lifted by a rope. The job is done in 10 seconds. So it's not just about how much work is done, but how quickly is that work done, how much power was delivered in watts and in kilowatts. So maybe you're lifting this box with some kind of motor. We want to know whether the motor is strong enough to lift the box in a certain amount of time. So it's actually kind of a two-step problem, right? We cannot calculate our power directly yet. Power is work divided by time, and they didn't give us the work. They gave us the time, but they did not give us the work. But they gave us the pieces we needed to get the work, right? Work is force times distance, and then power is work divided by time. So our work equals our force, the weight of the box, times the distance we lifted the box. Multiply those together, we find 11,500 joules of work. Now that we've got our work, we can do work divided by time equals our power. 11,500 joules divided by 10, that's 1,150 watts of power that were generated, that was delivered to lift that box. Somebody had to generate the power, but we're not sure who was lifting the rope. But we know that's how much power went into the box to cause it to be lifted in that amount of time. Now, we could have done it with less power. Right? If we want that power number to go down, we just have to make the time bigger. So if we lifted it in 20 seconds instead of 10 seconds, it would only been 575 watts. If we lifted it in 100 seconds instead of 10 seconds, it would only been 1,115 or 115 watts. So we can drive the power number down by increasing the time. And just an example, we're going to talk about this a little bit more later, but the idea of a roller coaster, right? They drag you up to the top of the roller coaster relatively slowly so that they don't have to, they're putting a lot of energy into you, right? They're putting you up at a great height, which gives you a lot of energy, but they're doing it very slowly so they don't have to do it all at once. Doing things all at once is what is difficult for us to do. And you contrast that, if you've ever been to the Six Flags in Eureka, Missouri, with the Mr. Freeze, where they do it all at once, right? You don't get slowly dragged to the top of a big hill and then dropped. With Mr. Freeze, they strap you in and you go from 0 to 70 or whatever it is in some short amount of time. And that particular ride uses a large amount of power, a large amount of electrical power. They're using electromagnetic motors to accelerate you in that circumstance. And it's a significant expense for them relative to their other roller coasters. Also a significant draw to the people who want to come to the amusement park. But that's kind of where power is at, right? It's all about the rate. How quickly does this stuff get done? If we want to do it quick, it's going to take a lot of power. If we're willing to let it happen slower, we don't need as much power. We were supposed to solve it for it in watts and in kilowatts. So we have the watts number. We want it in kilowatts. Well, 1,000 watts is 1 kilowatt. So we take our 1,150 and we divide it by 1,000, we get 1.15 kilowatts. Second example question, similar to the first, only we're going to go the other direction. The first time they told us the weight of the object and the time and the distance, and they wanted to know the power. This time they tell us the power of the electric motor, and they want to know what the weight of the elevator is. Again, we're given distance and time. So again, it's a two-part problem. It's these same two simple equations: work equals FD, power equals work divided by time. This time we're going to go in the opposite direction, right? We start with power and our goal is to find force. So we're going to use power to find the work. And then once we have the work and the distance, we can do work divided by distance to get the force. So we rearrange this equation. We bring the t to the other side. We have work equals PT. Here's our power from the problem, 65 kilowatts, which is 65,000 watts, times the time, which was 35 seconds. We get 2.275 million joules, or 2 million joules of work. And then we can do the second part, right? If the work is 2 million joules and we don't know the force, but the distance is 20 meters, then we do our 2 million joules divided by 20. And we get, keep clicking, and clicking doesn't work because I'm drawing. We end up getting our force of 115,715 newtons. Now, if you just done the whole problem with the 65 instead of converting the 65 to 65,000, all the math would have worked out the same. You would have ended up with 113.75 kilonewtons, thousands of newtons. We don't usually talk in that way, but we could if we wanted to. So those are some power practice problems. Go back and take a look at them. If they are not clear to you, watch as I go through them a second time. Perhaps that'll help it be clearer to you. So now we need to watch the next 5 minutes of that Eureka video that you watched on work. The middle 5 minutes are about kinetic energy. You'll notice the title of the slide says mechanical energy, and yet we're going to talk about kinetic energy. Both kinetic and potential energy both fall under a wider umbrella called mechanical energy. So they're both mechanical energy. The definition of mechanical in this context is something that has to do with motion or position. And so we're talking about kinetic energy, which is energy of motion. We'll talk about the energy of position in a little bit. I like to point out to my students, the mechanic works on your car when the moving parts of your car have issues. Somebody else works on your car if it's the non-moving part, right? If you shatter your windshield, you don't take it to a mechanic, you take it to a glass guy. If you have a dent in the side of your car, you take it to an auto body guy. You don't take it to the mechanic. The mechanic works on the engine, the moving parts of your car if you have that issue. So energy of motion, kinetic energy, you saw in the video, they talked about kinetic being the Greek word for movement, from which we get kinesiology, which is the study of human motion. We get cinema, which is moving pictures, but we keep the K in physics, so we have kinetic energy, which is the energy of motion. That becomes very obvious when you look at the equation. 1/2 m, the mass, so how much mass we have determines how much energy, right? If I throw a baseball at you, it's going to have more energy than if I throw a tennis ball at you with the same speed, because mass does have a role to play, but then the velocity has a bigger role to play. Velocity squared, and that's a big deal. That square is going to be very important. It's going to come back over and over in this chapter and future chapters to be very, very important. The velocity is squared when it goes in the kinetic energy equation. This is why they tell you things like speed kills, right? Because if your velocity doubles, right, twice the velocity is getting squared, and now we have the v squared, but we have the 2 squared. So if you double your velocity, you end up with 4 times the kinetic energy. If you triple your velocity, you end up with 9 times the kinetic energy. So as your velocity goes up, your energy goes up even quicker, and we're going to talk about why that's really important in a few moments. So yes, directly dependent on mass, but on the square of the velocity. And here we just have a picture of the pool balls, which they talked about in the video, just a good example of objects having energy and being moved around because they have energy. And the other thing they talked about in the video was the connection between kinetic energy and work. And that's called the work kinetic energy theorem. It's a lot of fancy words to say this very simple mathematical thing, which says that if we do work on something, if we apply a force through a distance, that object is going to gain energy from that work, and therefore its energy is going to go up. On the other hand, if an object that's moving applies a force through some distance, it's going to give up its energy to apply that force, and so its energy is going to go down. Again, it's a very useful way to think about friction in the world around us, right? So I take a tennis ball or something and I throw it through the air, and we say, well, the air slows it down. There's air resistance. Well, what does that actually look like? Well, there's some friction force from the air, and the further it travels through, the greater distance it travels with that friction force, the more work is taken away from it, right? So again, something as simple as a baseball pitch going from the pitcher's mound to home plate is going to lose a lot of its energy, or not a lot, it's going to lose some of its energy on the way, and that's because of the work being done by friction on the object. So some objects get a lot of energy stored up in them because we do a lot of work, right? We might do that a lot of work quickly, we might do that a lot of work slowly, right? They built these towers. They built these towers over a number of years, but they had to lift, right? They lifted objects. They applied an upward force through some distance. They lifted all that steel, all that material up to a great height. They stored a lot of, they did a lot of work on it, and it stored a lot of that energy for a long time. And then when the towers fell, all that energy got turned into kinetic energy, and it came down very fast and with a lot of energy. That gets into potential energy, which we haven't talked about yet, but we'll get to in a moment. The easier example to think about is the car, right? We step on the gas. We do work on our car by using chemical energy, by exploding gases inside our engine block to push the piston, to do work on the piston, and that makes our car go faster and faster, right? And if you speed your car up to a great high speed, your car is now full of energy, and in order for your energy to go away, you're going to have to do work on something. There's going to have to be something done to take that energy away. And again, we talked sort of about this idea in the momentum chapter about how you got to stop it somehow, and if you want to stop it in a safe and a gentle way, you're going to have to increase the time to make the impulse more gentle. Here we talk about increasing the distance over which we stop so that the force is smaller, right? And we have that discussion about trains, right? Trains take a certain distance to stop because their brakes are just limited in how much force they can apply, and therefore how much work the brakes can do. And the train has an enormous mass, and if it's going, you know, they always talk about that, a 100-car freight train going 70 miles an hour takes over a mile to stop. Well, that 70 miles an hour is very significant, right? Because again, it's one half mv squared. So if the freight train has a huge mass, yes, but it also has a big velocity. If the freight train was going a lot slower, it would not take as long to stop. But here's one of the very, very important key equations we're going to use over and over in this chapter: work equals change in energy. What units do we put work and energy in? They have the same units. They're equivalent to one another, so they're going to need to have the same units. Similar to how impulse and momentum had the same units because they were set equal to one another as well. So if you look carefully at this, we've got mass, which would be a kilogram, right? That's our standard unit for mass in this course. We have velocity, which would be meters per second, but we're squaring that velocity. So we square the meters and we square the seconds, and the kilogram goes on top. So we have kilogram meters squared over seconds squared, and that's a lot to say, that's a lot to deal with, and so we have something that we put in its place. A joule is defined as 1 kilogram meter squared per second squared. That's the definition of a joule. And if you look at the work equation, it works out the same way. A Newton was a kilogram meter seconds squared. So we're going to multiply that by another meter. So a meter times a meter would be meters squared. So now we're back to kilogram meters squared over seconds squared. We're back where we started. So work equals force times distance. Kinetic energy equals 1/2 mv squared. You might wonder about this spelling of joule. It's not how we normally spell joule, but it's because it's named after a person. This particular person, he was a physicist. He was also a brewer of beer, and he is famous in physics for showing that the energy that we're talking about now, the mechanical energy that's kinetic or potential, is actually the same energy as the energy we associate with temperature. They're just in different forms, but they are equivalent. So you see here sitting on his desk, he had this device where he let a mass fall. So its kinetic energy as it was falling would go into spinning some paddles, and those paddles would warm up the water, and he was able to show that the amount of energy that went into the water to cause its temperature went up was the same as what had gone out of the block. Just kind of strange serendipities of history and of knowledge. The reason he was able to do this experiment first and better than other physicists was because as a brewer, he had these incredibly accurate thermometers that he needed for brewing his beer. And so he had them to do physics on the weekends in his basement. So we talked about work, we talked about power, we talked about kinetic energy. Now we're going to talk about potential energy. So go ahead and watch the last 5 minutes of that Eureka video. See what they have to say about potential. So potential, you know, I talk about this word potential with my high school students. It's about possibility, right? That's what the word means in our English language, and that's what it means here as well. It's about the possibility of doing work, or really of moving is usually how we think about it. We talk about what's possible in the future. So we don't talk about a 90-year-old person's potential necessarily, but we might talk about a 15 or a 20-year-old person's potential because they have a lot of possibilities ahead of them. So gravitational potential is the possibility you have of gaining velocity because you're above the ground. So we call this gravitational potential energy, and many times when people say PE, this is what they mean. They mean gravitational potential energy. I have a little g down here to denote that it is gravitational potential. We're going to talk on the next slide about the other type of potential energy, but most of the time, when we talk about potential energy, we're talking about gravitational potential energy. And it's a combination of three things. Again, mass. A baseball is going to have more potential than a tennis ball held at the same height. It depends on your gravity, right? If I went to the moon, there would not be the same potential to fall because the moon pulls things down slower. So you're going to hit the ground at a slower speed than you would on the Earth because the gravity pull is not as much. Again, this aspect's not going to change, right? We know here on the Earth, little g is 9.8, and so that part we're going to tend to start forgetting about or ignoring because it tends to be the same all the time. But if you would go other places, that part would change. So the more massive you are, the have more potential, and then obviously the more height you have. And again, on Earth, our mass rarely changes, our gravity rarely changes, so gravitational potential often comes down to an analysis of your height, right? If your gravitational potential doubles, it means your height's doubled, okay? And similar to the video that we just saw, right, a rock on the edge of a cliff has this potential, has this possibility of rolling down the hill and having some kinetic energy when it gets there and maybe applying a force through a distance. So it's got the potential. If the same rock was at the bottom of the valley, we might say it has no more potential because it can't fall any further. It's already as low as it can go. So we can actually re-examine the problems that we've done in the past, problems we did back in chapter 4 about throwing things up in the air. We can re-examine them in light of energy, right? When I take a baseball and I chuck it up in the air, I have to do some work. I have to apply a force through a distance to make that ball move. And so that work that I do immediately gets converted into kinetic energy. So then it's going up with some kinetic energy. But as it goes up, its height gets bigger and gravity slows it down. So it's converting its motion energy into position energy until when it gets to the top, It's got all position energy. It's run totally out of kinetic energy. It's run totally out of work. I mean, the work stopped as soon as it left my hand. And then it falls back down, and the potential energy is converted back into kinetic until it gets down here with the same kinetic energy that I tossed it at. And if my hand's still there, it will apply a force to my hand through a distance. It will do some work on my hand. And that's, you know, again, that's one thing when it's a baseball. It's another thing when you shoot a bullet out of a gun and it goes straight up and it comes down and wants to do work on you like it just came out of the muzzle. So the other type of potential energy that we're going to talk about is called elastic potential energy. And again, it's still energy of position, but it's energy that's stored in making the position different from normal. So we think about this in terms of springs. Springs have something called a spring constant, and if we stretch the spring, there's energy stored in the spring, and when we release that spring, that energy will come back out. A rubber band's a really simple example that everybody intuitively understands from their life experience, right? If somebody is stretching a rubber band out right in front of your nose, you know to be nervous. The rubber band's not moving, but you know it has the possibility of moving and smacking you in the face, and you really don't want that to happen. And so we understand the risk of that potential. So the elastic potential equation is 1/2 kx squared, where K is the spring constant, right? You have tight springs, you have loose springs, you have tight rubber bands, loose rubber bands. So that K value varies on the material, but we call it the spring constant because for a given material, it tends to stay constant. And then we have X, which is how far we're stretched away from normal, So if we have a spring and it's just sitting sideways on the table and it's not stretched at all, then you're not going to have any X. X will be 0. There's no energy stored in the spring. But if we stretch it a centimeter, if we stretch it an inch, then you start talking about energy being stored in the spring. So why do we care so much about energy? How does this make our life easier? Well, the bottom line is that we don't have to deal with the collision, right? In momentum, the goal was not to deal with the collision. Here, we don't have to deal with the collision. We don't even have to deal with the path. We don't even care how you got from point A to point B. If I can measure your velocity at point A, if I can measure your velocity at point B, if I can measure your height at point A and at point B, then I'm done. That's all that I need. So the path doesn't matter. The path doesn't matter. So if the ball were to be dropped off of this hill, or if we set the ball on this ramp and it slid down the hill, which ball would be going faster, the one we dropped or the one that slid down the hill? The reality is that they would, if there was no friction, they would reach the bottom with the same amount of energy and would have the ability to do the same work. The direction of their motion would be different, right? This one's velocity is all going to be straight down as it comes down to hit the ground. And this one is going to be sliding at an angle, which is going to be a little bit different. But fundamentally, the energy is the same. Now, assuming no friction is a pretty big assumption. I understand that. But there's going to be lots of circumstances where that's a reasonable assumption to get us an approximate answer. And so the path doesn't matter. The path doesn't matter. We don't care if a airplane does all kinds of funky gymnastics, but ends up here 500 meters above where it started, then I can say something about its energy, or not an airplane. Okay, so I said that wrong. The airplane would be getting more energy from its chemical engines. If this was a glider and it did all kinds of funky aerodynamics and got up here, I would be able to say something about how much slower it was going based on its gain of height. And if instead it had gone down that much, I could say something about its loss of height and therefore gain in velocity. So I just think the big ball machine at the Science Center is just a great example of, you know, the path doesn't matter. They've got that little hamster wheel at the bottom. The kids can get in. They run around the hamster wheel. It takes all the balls up to the top, and they all get released from the same height up there. But then they follow a variety of different paths and jumps and turns and spins and all of this thing, and then they end up back at the bottom, back with zero height again after they've run out of all their energy. And again, that energy would never have run out. They would go down to the bottom just at the same speed that they'd been dropped at, or the same speed a ball dropped from the top would reach the bottom if there was no friction. Now, again, obviously in this device, there's friction. There needs to be friction. We don't want the balls all coming out at the bottom at that incredibly high speed. But again, the path doesn't matter when we're looking at things in a energy standpoint if we're ignoring the friction or if the friction is small enough to be neglected. So this is what we call a conservation law, right? We had conservation with momentum. The momentum before equal to momentum after within certain rules. And the same thing is true with energy. Within a closed isolated system, the energy changes form, but the total amount is constant. Very similar to the restrictions we had for momentum. The difference here, momentum didn't tell us anything about height. Momentum was great about two cars on a horizontal track. Momentum was not so helpful for things that were going up and down and side to side. Energy has something to say about the up and down because it's got the gravitational potential, which measures the height. But the conservation law looks a lot the same, right? It's the same principle. You can't create or destroy energy. As I talked already, the dollar example, if we each had a certain amount of money and we were locked in a room and started playing poker, the money would change hands. Some people get richer, some people get poorer, but the total amount in the room would not change. That's what conservation means. So we had momentum before equaled momentum after. Now we're going to have energy before equals energy after, only we've got a couple different forms of energy. We've got potential energy, kinetic energy. So we've got potential energy, what's its height, and how much energy does it have associated with that beforehand, what's its velocity beforehand, and then what's its potential based on its height afterward, and its kinetic energy afterward. And if there's friction, that part's got to get added here to the right side. And if we think about that for a moment, it will make sense to us. That energy has to come from somewhere, right? And it's going away. It's being, quote, lost to us. It's not going to be available to turn back into motion or back into height anymore. It's actually getting turned into heat, which is part of the story that Joule was pursuing and was telling with his experiments. But so it needs to be lost, right? You could think about something like, say, if we had 200 joules of energy total here on the right, on the left, and then through the process of our ball rolling around the ramps or whatever, 5 joules were lost to friction, right? So we should have another 195 joules left over here because we started with 200 and 5 of them are in friction, so we have 195 left. So we would add the work to this side, or we could subtract it from the before side, but no, we don't like subtraction sides. So we're going to leave it over here where it can be added. So, and this looks a little confusing or a little complicated maybe because there's 5 terms here. But the beauty of these problems is very often that one's going to be 0, the work's going to be 0, and a lot of times 2 of the other ones are going to be 0 too. If you think of something as simple as a child sliding down a slide, right? Well, at the top of the slide, he has some big height, but he's basically not moving at the start. And at the bottom of the slide, he basically has no height, right? If we measure the height from the ground, the slide comes out on the ground. And so we end up with a 0 here, and a 0 here, and a 0 here. And so my problem, which had 5 terms, simplifies down into the before energy potential equals the after energy kinetic. And then we can replace those with the corresponding individual equations. MGH for potential, 1/2 mv squared for kinetic. And then we can notice even one more simplification, right? This is the mass of the object, and this is the mass of the object. So if the mass of the object is on both sides, we can divide both sides by the m, and the m drops out. So if the m drops out, or at the very least the mass stays constant, so it's not going to be affecting things too terribly much, and g is constant, it's really about the comparison of your height to your velocity. As your height goes up, your velocity goes down, right? Think of a baseball being tossed up in the air. And then as your height decreases, your velocity increases. Think of the baseball falling back down, or the kid going down the slide, or the roller coaster going down the big first ramp, or the bungee jump. Lots of different examples of something falling, and as it falls, it speeds up and loses height. So we can go back and forth between these three terms: work, potential energy, and kinetic energy. And this slide is just asking us to take a moment to think about some examples of how we could go from one to the other in everyday life. So work could be done to increase potential energy or kinetic energy. So again, work is us applying a force through a distance. So we could do work to increase potential energy, right? I could lift a book up and put it on a shelf. I apply an upward force through some distance. I increase the height of the book. I set it on the shelf. I've now done work. The potential energy of the book has gone up. So that's a great example, and you can think of 100 other examples, all under the category of lifting. If you lift something, you're doing work to increase potential energy. You just are. That's what lifting is. But you could also think of the other type of potential energy, right? I could apply a force through a distance to stretch a spring or stretch a rubber band. And so I'm applying a force through a distance, and that's putting energy into the rubber band, potential energy into the rubber band. Or you can do work to increase the kinetic energy. So this would be any type of object that you would, say, throw or pull, right? You're applying a force through a distance, and the object is moving, and potentially the more force you put through a distance, the faster the object is going to move, right? We talked about this a little bit with the impulse discussion, but I think it works even better here with work and kinetic energy. Pitcher's windup is all about him starting his throw with his arm stretched far out behind him and ending his throw with his arm stretched out far out in front of him, so that he's applying his force for the maximum distance. And you put on top of that the fact they like pitchers to be tall. The taller you are, the longer your arms, the greater that distance is. It's really all physics. They describe it in terms of coaching and sports, but it really comes back to physics, applying that force through a big enough distance. We had that discussion about the guns. The rifle is long, therefore the gunpowder explodes and pushes the bullet for a greater distance. That's work being done to give it kinetic energy. You have a smaller gun, and it's going to push it for a smaller distance and therefore give it less kinetic energy because of the differences in the length of the barrels. Potential energy or kinetic energy can be used to do work. So I picked that book up, I set it on the shelf, right? If I take the book off of the shelf and I drop it onto, I don't know, what do you want to crush? I drop it onto a cardboard box, it can apply a force through a distance on that cardboard box and do work on the box and crush it, right? And the higher I drop the book from, the more it will crush the box, the more work it will do to the box. Kinetic energy can be used to do work as well. Again, any moving object that runs into resistance, it's going to push against it with a force, and it's going to push for some distance with that force, and so it's going to do work. Again, something as simple as the baseball being thrown and the batter misses and it hits the catcher's glove, and it applies a force through a distance into the catcher's glove, and so it does work on the catcher's hand. And if his hand catches it wrong, he can the work can be done, the force can be applied in such a way that he breaks a finger. But you can think of many, many examples of a moving object striking something and applying a force to it, right? And that force, if it's able to move it any distance, is going to do work. And even things that we think of as immovable are oftentimes being moved. Interesting experiments, you just take a laser pointer and you duct tape it to the wall, perpendicular to the wall, so it's pointing across the room. And then you take that wall and you just lean on it, lean on the whole wall with your weight, and see what happens to the laser dot that's shining across the room. You will notice that the wall's just not as solid as you thought it was. and potential energy going to kinetic and kinetic going to potential energy. That's what a lot of these next examples we're going to talk about are all about. We already talked about tossing the baseball up in the air. It starts out as kinetic, turns into potential, comes back to kinetic from the potential. We talked about the work kinetic energy theorem. It's oftentimes called the work, well, like I said, the work kinetic energy theorem. Practically, we can use it to just be the work energy theorem. We can say work equals change in potential energy. That's okay. The reality is, though, you can't lose potential. Your height can't change unless you move. So when I drop a book on a cardboard box, you know, I can say, hey, whatever potential energy the book started with, that's how much work gets done to the box, and that's totally correct. But the actual mechanics of it happening is the book has to fall, its height has to be converted into velocity, and then it has to hit the box with that velocity to be able to do work. You can't do work if you're not moving. It's just a reality. You can't apply a force through a distance if you don't move that distance to apply the force. And so it really has to go through the path of kinetic energy. But for our mathematics, that's not necessary. So one of the great examples of kinetic and potential is a pendulum, right? So here we have a ball on a rod, and you guys did that experiment in class, in lab, the last time we were actually physically together, when we found out we weren't probably going to be physically together again for the rest of the semester. So you have this ball on, and it can be a rod or a string, it doesn't matter. We hold it up here to a great height. So it has a lot of potential energy, and we haven't let go of it yet, so it is not moving, so it doesn't have any kinetic energy. But we let go, and it begins to swing down, right? Gravity pulls it down, and as it comes down, it loses some potential, and that potential gets converted into kinetic. And you could sit there and go, but Mr. Essie, we learned that the pendulum falls and swings because of gravity. Does it fall because of gravity or because of energy? It's all one and the same, right? It falls because there's a force pulling on it. But energy allows us to analyze it and make predictions about what's going to happen next more easily than just using the gravitational force, right? Because the gravitational force here is always going to be pulling straight down, right? Straight down on the object, and that's going to get a little complicated, right? We're going to have to use those angles. You guys don't want to use angles, I know that. So it's easier to think about it in energy than to reanalyze it in forces. Not that you can't do it with forces, it's just easier to do with energy. And we're about an easy solution if it's available to us. So you started out here in the highest position, you end up in the middle position. The middle position of a pendulum will always be the low position, right? Because we've got that thing stretched out as far as we can go toward the earth, and we didn't make it. So went from all potential to all kinetic. In the middle, we were some of each, and we will swing all the way back up on the other side to exactly the same height we started at, because all of that potential we started with gets fully converted to kinetic and then fully converted back to potential as we slide back up. Again, this is assuming no air. If we have air, if you have a real pendulum and you set it swinging, you notice that eventually it stops, right? I have a pendulum clock in my house, and it has these weights that hang from it, and the pendulum swings there all day, but the weight slowly gets lower and lower because that weight is maintaining the tension that keeps the pendulum swinging, and therefore it falls, it loses energy to keep the pendulum swinging, and every 3 or 4 days I got to lift the weight back up so that my clock works. And when I go away for spring break, then when I come home, the clock is not running anymore and the weight has fallen all the way to the ground. It's an excellent example of this energy conservation idea. So we just talked about pendulums and how they work. Another great example is pole vaulting from our days in track and field. So the man's running down the track with kinetic energy in this particularly in the horizontal direction. He plants his pole, right? And he bends the pole bends. And so a lot of the energy he had goes into the pole as he plants it and pushes against it and bends the pole. So we go from horizontal kinetic to elastic potential in the bent pole. And then as the pole unbends, it's turning his sideways kinetic energy into upwards kinetic energy. And that upward kinetic energy causes him to gain gravitational potential energy. And so we go from horizontal kinetic to elastic potential to vertical kinetic to vertical gravitational potential. And then as he clears the rod, he's not going very fast, right? The energy has been converted into his height, and he wants to high jump as high as he can over that bar. He even goes over the bar in such a way that his center of mass, remember we discussed that last chapter, his center of mass might not ever get over the bar, but his body gets over the bar, and his center of mass, you know, ultimately the energy is about his center of mass. So even if his center of mass doesn't get over the bar, if he can shape his body in the right way, he can go over the bar and get a pass without his center of mass going over the bar. And then what happens, right? The picture ends here. He's all gravitational potential, but he's over the bar. So now gravity is going to pull him down, right? And it's going to pull him down. I don't know what these heights are. I don't know how high they actually jump. I don't know if this is reasonably accurate or not, but he looks pretty high to me, and I sure wouldn't want to fall from that height and hit the ground because, right, my gravitational potential is going to turn into kinetic, and then the ground is going to say, hi. The ground is going to apply some force through a short distance, right? If I just hit the bare ground, it's going to stop me in a very short distance. It's going to use a large force. Something on me is going to break. But he's got this big cushion, right? And part of the key to this cushion is that it's thick, right? Very thick, so he can fall into the mat or the cushion, and with that larger distance, then the force the cushion has to deliver is correspondingly smaller. Bungee jumping, another excellent example, and we're going to go to a, where did she go? There she is. We're going to go to this website here of that talks about bungee jumping. So just a little animation here of a person on top of a tower, 20-meter tall tower. We're not going to focus on the numbers so much. We could if we wanted to. Apparently, it's a 60-kilogram person. Therefore, the gravity force is 589. And we've got this slider here where we can adjust the person's K values. So the bungee cord is elastic, so it's going to contain elastic energy. And so if we change the K, we will change how much it stretches to store a certain amount of energy. But what I want to drive home is what's going to go on here on the right side. So we're just going to hit play so we can start our bungee jumper on his jump. And we live in this wonderful world where there is no friction, so our bungee jumper is going to get to go and go and go over and over and over again. And but what we have over here in our three little colors, green, blue, and red, is the energies, right? The green one is our kinetic energy. The blue one in the middle is our gravitational, see big G, PE, big gravitational potential energy is the blue, and then the elastic potential energy is the red. So you will notice that when he was all the way at the top, his energy was all gravitational, right? It was all because of his height of 20 meters. And then when he gets all the way to the bottom, his energy is all in the red one, right? He's got almost no height left, and hopefully he's got no velocity left, right? You don't want to jump off a 20-meter tower. That's like 7 stories. You don't want to jump off a 20-meter tower and be going full speed when you're near the ground. That's called, yeah, that's not good. That would be very harmful for you. But at the bottom, the energy is all stored in the bungee cord itself, and you can see that with these force arrows, right? Gravity is constantly pulling him down. What is the bungee cord doing? Well, that depends on how long the cord is. The more it's stretched, the bigger the restoring force will be. The less it's stretched, eventually that goes back to 0. So you see, we go back and forth, gravitational potential at 100 at the top, elastic at 100 at the bottom, and kinetic never really gets over about 50%, right? I mean, this is what you would expect from falling, but then the cord starts to stretch and take energy from both of them. So the kinetic energy gets up to about 50%, and then it goes back down. Speaks a little bit to like the classic movie, you know, James Bond type thing, right? Where they jump off with this bungee cord, and then when they're right at the bottom, they cut the cord and they fall a short distance and they roll away and they escape. Really what this shows us is that is theoretically possible, right? Down here at the bottom, the energy is all in the cord. So if you could cut the cord at just the right time, your bungee cord goes shooting up at some great speed. and smack somebody up there, but you would have almost no velocity and almost no gravitational potential, and so you could fall just a tiny distance safely and walk away. Of course, the key to that is being able to cut the cord at just the right time, because if you cut a little early or a little late, it'll be messy. Let's go back to those other examples. Roller coasters, we're going to look at some more images of that on the next slide. And then again, this principle of friction, which we talked about a couple of times. Friction comes in, it applies a force for some distance, and that's work done by friction, and it comes out of our conservation amount. Again, the example I used is we have 200 joules of energy and friction takes 5 of them away. Well, then we only have 195 left to play with between our available options of kinetic, potential, and potentially work of something else. So here's another example. This is called a pile driver. It's basically a hammer on a very large scale. They lift this heavy, massive object up to some height, and then they let it go, and it falls down, slams into the object that they're trying to drive into the ground. Many medium-sized buildings are built on this principle. They drive piles 30, 40, 50 feet into the ground. It's similar to a giant nail. You think about, you pound a nail halfway into a board and then you try to pull it out. Well, you can't pull it out because the wood is squeezing the nail, because the nail squeezed the wood out of the way, and so it's pushing back, Newton's third law. It's held there very tightly. We drive these steel piles 40, 50 feet into the ground, and we make a square or some shape of them, and then we build a building on top of that, and that building can be 5, 6, 7, 10 stories tall, and those piles are able to hold it up because the ground holds them in. But you got to drive those things down into the ground to make this work, and you do that with a pile driver, which again is ultimately taking potential energy. It converts into kinetic on the way down, and then it does work on the object. And you can do the same thing with a hammer and a nail, and you can figure out how much energy your hammer is delivering. If you drop the hammer instead of swing the hammer, it's more complicated. And finally, this is our last slide for this lecture. We'll go into a numerical example of a roller coaster at the beginning of next time. But a roller coaster is a great example of potential and kinetic energy back and forth, right? So they take you to this highest point. The first hill is always the highest hill. That's one of the principles of roller coaster building because of this energy consideration. And they drop you down that first drop, and you get going really, really fast, and you're going so fast that you have enough energy to go back up over the next hill, and then down and up and down, and maybe doing loops and different things, but always sliding along a track that's not quite frictionless, so you're always losing a little bit of energy. So even if you tried to make the second hill the same height as the first hill, you wouldn't quite get up that hill because you'd have lost some energy from friction. So each subsequent hill is lower than the one before until you get to the end of the coaster, and they have some kind of brakes to actually stop you and bring you in. The other part we talked about with roller coasters is this first part where they drag you up very slowly, especially compared to how fast you come down, very slowly, so that they are not, they're using the same amount of energy, but they're using the energy spread out over a longer period of time, which means they're using less power. And the motor they're using to power that, what's it called? I'm blanking on a moment on what you call that chain that drags you up there, the conveyor. The motor that drives that conveyor can be of lower power and use less electricity, and therefore potentially save them some money. Plus, you wouldn't want to give people whiplash on the way up. Okay, so that's the end of the first chapter, the first half of this chapter. A lot of the conceptual stuff has already been explained. We will talk about some numerical examples on a video that I'll release hopefully this weekend. That would be corresponding to the lecture next Tuesday. This one corresponds to the lecture on Thursday, April 2nd. And again, when we finish chapter 8, we will be ready for an exam. It's supposed to be an exam over chapters 5 through 8. So we'll talk more about how to do that later.